Okay, welcome back to the One Word Mind seminar. Today it's my pleasure to introduce Nicholas Boffi from Carnegie Mellon University. He is expert in differential model, and his work is impressive in the sense that it contains a lot of theory, but also it makes to be competitive competitive with industrial use. He has developed a lot of useful method and efficient methods. And so without further ado, today he's going to talk about few-step language modeling with flow maps. The floor is yours.
Awesome. Thanks for the introduction and thanks for the invitation. So today I'm going to tell you guys about some work we've been doing for language modeling from a continuous flow perspective. More generally, you can think of this as kind of discrete generative modeling from a continuous perspective. But we're going to kind of focus on language because that's maybe one of the most prominent applications. And if people are not super familiar with flows, we'll give an overview of flows, although we won't go into great detail. And then we'll also give some detail on the kind of a recent extension called flow maps, which is kind of a clever way to accelerate the solution of flows. But we're really going to mostly focus on kind of the discrete generative modeling paradigm. Okay, so let's first kind of motivate the problem. So at this point, it goes without saying that there's now so many successes of generative AI across domains. So this maybe first got put on everybody's radar when like these crazy text-to-image generative systems started coming out. We started seeing images like this. This was generated by Black Forest Labs Flux. It's a picture with caption like two bugs having a tea party. So you can now run inference on this model yourself, and it's kind of totally ridiculous that you can give it a caption like this and it can produce such a high quality image. At this point, we sort of take it for granted, but to me, it's still kind of completely mind blowing. We've now been moving kind of beyond these static images. For example, Meta made a movie generation model called Meta Movie Gen using the same kind of techniques. So this is like the caption is like an otter floating downstream, and you get this kind of beautiful movie. And then we've kind of been moving beyond demos more recently. So DeepMind recently released AlphaFold 3. This is a molecular generative model that can be used to search for candidate drugs, understand molecular structure, and can be used more generally in computational biology. This is a diffusion model that generates these structures. And similarly, Microsoft recently put out their MatterGen model, which is a diffusion model that generates material structures. Both of these applications I find super, super compelling because I think one way to view them is that we're kind of using the generative model to parameterize some kind of complex high-dimensional space, and then we can actually search over that space to solve design problems. And I think there's going to be huge technological applications of these ideas in the near term. So if you ask kind of how we got here to these many impressive demos, it's kind of been a convergence of ideas. So there's actually a very simple formulation of the problem that's being solved here from a mathematical perspective. I'm given a data set of samples, xi1, where I runs from 1 to n from a target distribution that I'll call rho 1. And then my goal is going to be to learn to draw a new sample, let's call it x hat 1, from that distribution rho 1. So this is a problem that's received a ton of attention over the years. So, I mean, this kind of first got put on the map for me in 2014 with the advent of GANs. These were very fast models, but quite hard to train. People then moved on to normalizing flows and continuous normalizing flows. From there, they moved on to denoising diffusion models, which were kind of the precursors to modern diffusion models. Then score-based stochastic differential equations, which are now kind of like the modern instantiation of diffusions. And then most recently, flow matching, rectified flow, and stochastic interpolants, which were kind of independently discovered at the same time by three different groups, one of which I was a part of. So this is kind of the technique that most of these generative models are based on now, like in particular, like Meta Movie Gen, Black Forest Labs Flux, some of these examples that I just gave on the previous slide. And this is the formulation that we're going to use in this talk. And as I said, I'll give a self-contained introduction to it if you're not familiar with it. If you look at this kind of progression here, historically, it turns out that there's kind of been a convergence on a key idea, which is that if you want to build a generative model, then you should learn to transport measure along a fixed connection between a prior rho 0, like a Gaussian, and the target rho 1. So here's kind of the picture that you should have in your head. I'm going to kind of draw a curve in the space of measures between rho 0, which is like, as I said, a Gaussian or whatever distribution that you want, but usually a Gaussian, and rho 1, which is the one I want to sample from. And then I'm going to try to somehow deform the measure to traverse along this curve. And in practice, I can make this happen by learning a velocity field that involves samples from one distribution onto another. So I gave you all these kind of example application domains that have been in some sense revolutionized by this paradigm. There's actually even more that I didn't list. So like, for example, robotic control, now state-of-the-art foundation models are based on this kind of formulation. In some sense, the only one that really hasn't been influenced at this stage is really language modeling, which is still kind of dominated by these sort of like autoregressive next token prediction style models like ChatGPT and Claude. So the central question that I want to ask today is, can we build a language model in this dynamical measure transport paradigm? And would this be a good idea? Would it actually be useful? Okay, so let's maybe focus on this latter question of like, would this be a good idea and would it be useful? So why would you care about using a flow for something like language generation? Well, the first point is that you can do parallel generation. So you can produce L tokens at once rather than one token at a time. And this allows your model to have sort of more intrinsic kind of like planning and reasoning built in. A second motivation is that you can get few step generation. So all part of this talk will be an explanation of this class of methods called flow maps that we've introduced. And this gives us a way to very efficiently distill generative models based on flows into just an operator that can generate samples in one or two evaluations of the neural network. And this gives a massive inference time speed up. So if we have a continuous formulation of language modeling, then we can generate many tokens at once very, very fast. And this can reduce inference costs dramatically. If we have access to this flow map, then we can actually look ahead exactly because we can jump to the endpoint. And oftentimes in generative modeling, what you actually want to do is leverage some kind of pre-trained reward model to actually guide the inference process to generate samples that are high reward in some sense. So these could be like images that look good to humans, or this could be language that sounds poetic. There's many different ways that you can define reward models. Could be molecules that are likely to be stable or that are easy to synthesize in the lab, things like that. And so being able to have this kind of accelerated inference process will let us more efficiently guide the generation and do things like RL-based fine-tuning more efficiently. So this lets us build generative models that are more steerable and more controllable. And last, there's some kind of a very conceptually appealing point, which is that if we can get continuous flows to work well for discrete modalities like language, then we kind of have one unified perspective across all modalities. So then we can do generative modeling for discrete data, continuous data. We can do images and text at the exact same time. We can do images and audio and text at the same time. You can do structure and sequence in protein modeling. You can do the molecular structure and the amino acid sequence at the same time, even though one is discrete and one is continuous. So you just have one differential equation that kind of generates everything at once. And I find this very, very appealing. Okay, so these are actually motivations that are often given for so-called discrete diffusion processes. So why not discrete diffusion? Well, there's actually a very simple reason, which is that much of what I gave, much of the arguments that I gave in the previous slide kind of centered around access to this accelerated inference in terms of a flow map. And it's actually much harder to do this with a discrete diffusion. So discrete diffusions and flows process the whole sequence of tokens at once. And that means that if we want to actually like compensate for this extra cost of processing the whole sequence at once, we actually need to reduce the number of sampling steps accordingly. So in practice, we typically have L tokens. We have a vocabulary of size V. And that means that the transition density that we need to estimate to sample from one of these discrete generative models is combinatorially large. So it's of size L to the V. So how do you deal with this? Well, in discrete diffusion, you typically factorize this density using kind of like a product of marginals or like a mean field style approximation. And this neglects intertoken correlations. So what this means in practice is you can construct kind of failure modes like the following. So if you look on the right, I'm showing you what happens if you take many steps with a discrete diffusion model. You can capture correlations like New York and San Diego. It turns out that this kind of factorization that is made is exact in the infinite step limit, so kind of in the continuous time limit. But as soon as you try to reduce to few steps, because you're doing this kind of marginal approximation, you cannot capture correlations and you can miss things like New York and San Diego, instead perhaps computing New Diego or San York. We can contrast this with what would happen with a continuous flow. So continuous flows can get the right answer with many steps in the same way as a discrete diffusion. But because a continuous flow defines a differential equation and that defines a unique diffeomorphism, I can just learn that diffeomorphism and then I can in fact just map to the endpoint directly in one or a few steps. And so even though I'm taking a small number of steps and it's computationally much more efficient, I can still capture these intertoken correlations. Okay, so at this point, this is all kind of hypothetical. So I want to kind of give you some foreshadowing into the final results that I'll actually end up at. So here I'm showing you a plot of the generative perplexity, which is kind of a standard metric to quantify the accuracy of generated text. Lower is better. And on this plot, I'm showing you our method, which is kind of the red dot in the bottom left, in comparison to many discrete diffusion baselines. And what we find is that we match every discrete diffusion baseline in quality, but we're 8.3 times faster. And in fact, that because we can distill into this flow map, our approach actually kind of maintains its performance across step counts. So other methods kind of fail catastrophically, and in the small step size regime, they start to have their complexity blow up in line with kind of the neglected correlations I showed you on the previous slide. We actually maintain performance kind of, and we have this flat red line. Okay, so that's kind of the overall setup and kind of, as I said, a foreshadowing of the results that we will obtain. Let's start trying to figure out how to actually design such a generative model. So to do so, we're going to use the stochastic interpolant framework. So here's the following definition. A stochastic interpolant is defined in the following way. I take a sample from my base density, like a Gaussian x0. I take a sample from the target, x1. And I take a linear combination of them with coefficients alpha and beta. And these guys need to satisfy some boundary conditions, namely alpha starts at 1 and ends at 0, and beta starts at 0 and ends at 1. Oops, sorry about that. Okay, because of the little mishap there, let's maybe just pause and make sure nobody got distracted and everybody can see these equations. So we take this interpolation, and these are just very general constructions that basically assume that I start at x0 and end at x1. Okay, so this is a very simple definition. What are the key properties? Well, first of all, it's an exact finite time connection. So at time t is equal to 0, because the boundary conditions, I get x0. At time t is equal to 1, I get x1. And everywhere in between, I have some sample, it, of some distribution, let's call it rho t. And that distribution just interpolates between rho 0 and rho 1. And it does so exactly on the time interval 0, 1. So it's unlike a diffusion model, which actually takes infinite time to converge. It's easy to sample, so I can just compute IT explicitly using my samples x0 and x1. So I can just calculate this thing, no problem. The base distribution here is arbitrary, and in fact, it can be tailored to rho 1. So if I have some domain knowledge, I can actually construct a distribution that is based on the target distribution, and I can use this to improve performance. This is particularly useful in things like inverse problems that arise in computer vision or in scientific computing. We have several papers on that. And in fact, it's super general. It includes diffusions, flow matching, etc., as a special case. Okay, so here's the picture you should have in mind. So here my base density is, say, the distribution over white flowers, and my target density is the distribution over purple flowers or the Gaussian. So in the top, I'm showing how my white flower deforms to a purple flower and has a bit of noise in the middle. In the middle row, I'm showing you a different definition of the interpolant where I devolve to pure noise in the middle. And in the bottom row, I'm showing you kind of the standard sort of flow matching interpolant where I devolve just to pure Gaussian noise. And again, this is kind of like a diffusion model, but it happens exactly on finite time. So the magical thing about this construction is that I have this simple interpretation at the level of the samples, but when I do so, I actually define some kind of time-dependent measure at the level of a distribution. And in fact, this time-dependent measure evolves continuously, and I can actually quantify its evolution. So if you're an applied mathematician like me and you look at this video, this feels like something that's evolving according to a PDE, something like a transport equation. And in fact, you can prove that the time-dependent density, rho t, of the interpolant indeed solves a transport equation. So here's the equation here, dt rho t plus div bt rho t equals 0, where bt is the conditional expectation of the time derivative of the interpolant. So what this means is if I want to know how the distribution is going to evolve at a given point in space, I look at all the interpolants that travel through that point, all these kind of straight lines that go through that point, and I average all of their slopes, average all their instantaneous velocities, and that gives me the velocity that acts at the level of the measure itself. Okay, so in practice, I'm going to use this construction to build a generative model, and so I'm going to need to learn an estimate of this guy. But in fact, it's very easy to learn this guy because it's defined in terms of a conditional expectation. So I can just learn it via square loss regression. It's a very simple result, sometimes called the fundamental theorem of machine learning, that the Bayes optimal predictor for a regression problem is a posterior mean, like this. So I can just solve this L2 regression problem, for example, representing B hat as a neural network, and the optimal solution will be precisely this conditional expectation. And then to form my generative model, what I do is I just solve this transport equation via the method of characteristics. So I look at it, the so-called probability flow, ODE. This is an ordinary differential equation whose right-hand side is the velocity field B. I draw an initial condition x0 from rho 0, and then I solve this guy up to time 1. And I have the property that at time 1, I get a sample from rho 1. So what this construction does is it converts the generative modeling problem into a problem of regression followed by a problem of solving an ordinary differential equation, both of which I actually know how to do. And as I said at the start, this simple approach is now state of the art across many domains, ranging from molecules to materials to images to video to robotic action models. Okay, so given this setup, what I want to ask now is how can we extend this from continuous modalities to discrete data, and in particular language? Okay, so how are we going to do this? Well, let's first define our space. So we're going to have a vocabulary of size V, and we're going to assume that we're going to model sequences of length L. And that means that a single sample of language data is going to be in V to the L. Okay, now the difficulty with this is that it's discrete. And so it's not obvious at all how to do that construction that I used before. In particular, I cannot draw lines between discrete data. So what I need is some kind of continuous embedding of the data. So what I'm going to do is I'm going to do kind of the simplest, most trivial embedding. I'm just going to one-hot encode the data. So what this means is that every discrete token gets assigned a vertex on the simplex. They're all just like unit vectors, basically, at the end of the day. And one kind of key property of this embedding, while it's not like semantically meaningful in the sense that the L2 distance between any two tokens is just one, it's lossless because I can always recover the data just by argmaxing. Okay, and then I'm going to draw a simple linear interpolant in this space. So I'm going to start from a Gaussian, which is N0I, and then I'm just going to interpolate to the target. So this is the picture that you should have in mind. I'm going to use this kind of running example where I have a vocabulary of size 3. So my simplex is just like a triangle, basically. And the vertices are just going to be CMU totally rocks. That's my entire vocabulary. And what you see here is that I start from a Gaussian, and this Gaussian kind of contracts onto the vertices. Okay, so now we can kind of push this further with this simple construction. So I could try to do flow matching with this linear interpolant. That's just this regression problem that I wrote down before. But the difficulty with this is that it somehow like mixes the discrete data with noise. So here x1 is a unit vector because it's this kind of canonical one-hot embedding of the discrete data, and x0 is Gaussian noise. And so this x0 is kind of just like destroying all of the low-rank structure, and like this L2 regression, like it's not very sensitive to the fact that the data is one-hot. And so it turns out this doesn't really work. If you naively just try to minimize this loss, you actually don't really get something that generates data very effectively. Okay, so we can use some insight from what has appeared in the literature. And in fact, it turns out that for things like protein models and actually arguably even for images, it's a much better idea to learn the so-called denoiser, which is the posterior mean of the data, given that I'm at a fixed point in space. Okay, and the reason this can be useful is because it actually somehow knows about the structure of the data, because you're estimating x1 itself rather than estimating the flow. So in particular, in this case, we're estimating something that is an average of one-hots rather than estimating rather than trying to estimate this flow that needs to converge to one-hots. At the end of the day, we need the flow because we want to actually integrate the equation. But in fact, there's a simple relation that lets us convert this denoiser into a flow. So if we learn the denoiser, then we can just convert it into a flow, and we can just integrate that guy. Okay, it's singular at time 1, but it actually doesn't really matter because in particular, if I integrate this guy with Euler, I never actually evaluate the right-hand side at time t is equal to 1. And actually, the singularity can help you converge to the manifold of data since you kind of need to get to these discrete vertices at the end of the day. Okay, so here's the picture that you should have now. So we're trying to learn a time-dependent flow field that's defined over the whole space but converges to the vertices of the simplex. And we're going to do so by learning this denoiser and converting it into a flow with this simple relation. Okay, so how can we learn the denoiser? Well, it is also a posterior mean. And so that means that I can learn it via regression. I can just solve this L2 regression problem that I've written here. But this also has a problem, if you think about it, because the square error is not like adapted to this one-hot encoding. Like the one-hot encoding is between 0 and 1. And like it's, you should maybe really think of it as a probability distribution. And somehow like L2 is just not really like the right metric to use on probability distributions. It's like quite insensitive. And, in particular, because when you square numbers that are between 0 and 1, they become smaller. It's kind of doing this weird sort of like compression to the unit interval. And it's not really what we want. In some sense, what we want is something like the opposite. We kind of want to expand the unit interval to be over a larger interval so that we can actually compare differences more effectively. Okay, so if you think about it, what I'm really saying is we would like to use something that's a bit more like cross entropy or a bit more like KL, but it's not actually clear how to do so. It turns out that in this one-hot encoding setting, there's a very nice probabilistic viewpoint, which is that this denoiser is actually a probability distribution. In fact, it's the posterior density. Okay, so the denoiser at a given point x is not only the posterior mean of the data, it's the posterior density of the data. It's telling me what is the probability to end at a given token, given that my interpolant is at a given point in space. So now here's the picture you should have in mind. The denoiser can be converted into a velocity field, but it is always kind of capturing my posterior density over where I believe I'm going to go. Okay, so it's always kind of a probability distribution over the vertices, and this distribution is changing over time, depending on where I'm at. Okay, so now I've shown that this denoiser is a probability distribution, and that suggests that maybe I can actually learn it with cross entropy. And in fact, it turns out that you can. So I'm not going to prove it here. The proof is in the paper. But if you write down this cross entropy objective function, which is kind of just like, minimizing the negative log likelihood of the data, then the global minimizer is precisely the posterior density, which is precisely that denoiser. Okay, so this is all very interesting. And it says that I have a way to, instead of learning with square error, to learn with cross entropy, which should be more adapted to the data. It turns out there's kind of an interesting interpretation of this problem, which is that it's actually a token classification problem. So what this loss is saying is that I need to basically identify the decision boundaries. I need to figure out at any given time, where am I slicing the space to determine where my interpolant is actually going to go. Okay, so this is all great, and this gives me a way to learn a flow. I'll minimize cross entropy to learn my denoiser. I'll take my denoiser, I'll convert it into a flow, and then I can integrate that flow. And in principle, I can do generative modeling. In fact, this still doesn't work as written, and it ends up being kind of a subtle issue. It's because the way I've written this cross entropy objective function, I have an integral from 0 to 1 in time. And so I'm actually sampling time uniformly. You can kind of view this as a random an expectation over time where time is drawn uniformly from 0 to 1. So why is this a bad idea? Well, we're going to define a new quantity that we call the decoding error rate. Okay, this is worth like pausing on for a minute. This probability here is the probability that the argmax at time t of the interpolant is not equal to the argmax at time 1. In other words, if I'm at a given time t and I round to the nearest vertex, or to the most likely vertex, say, do I get the right answer or do I get the wrong answer? I'm going to sum that over the whole sequence and average it to understand what is the rate that I'm making errors at time t. And it turns out that this error rate is kind of distributed highly non-uniformly throughout space. Okay, so if you sample time uniformly, you end up sort of wasting a lot of time when either everything is wrong or everything is right. And what you really need to resolve, in some sense, is when these guys are crossing decision boundaries. So you need to understand when is the model flipping from kind of the wrong token to the right token. These are kind of sensitive regions. And you need to be able to sample time more aggressively in those regions. So how can we do this? Well, we're going to define a reparameterization of time. Okay, it turns out that this is the right reparameterization of time to uniformly distribute the decoding error. What we would like is a definition of time such that when I move incrementally, if I move like order 1 in time, then it changes the decoding error by order 1. And it does so kind of like uniformly throughout all of time. So you can look at the paper as to why this is the right way to reparameterize time, but you can kind of see it graphically by looking at this figure here. So they're solid curves. These are the decoding error as a function of time and as a function of vocabulary size. And what I'm showing is that as you increase the vocabulary size, the decoding error becomes sharper and sharper. It basically becomes the case that you're wrong for a really long time, and then you suddenly flip, and then you start getting it right. Okay, so a lot of action happens in one specific region. Okay, so the larger the vocabulary, the more significant this problem actually is. When you reparameterize time, as we've done, you see these dashed lines, and here you see that the decoding error is kind of uniformly distributed. Okay, so here's kind of a movie of what I'm actually saying. So I literally use this formula to reparameterize the frame rate here, so you can visualize what's actually happening. to make it a little bit more exaggerated, because the effect is not so big for v is equal to 3, which I'm using on the right, I'm using v is equal to 10,000 or something like that. But what you can see is that I've sort of warped time so that everything slows down while any of the interpolants are wrong. And I go in kind of slow motion until everybody's right, and then I move fast again. And I move fast when everybody's right beforehand as well, or when everybody's wrong in the beginning. Okay, so I'm really just trying to resample time when some people are right and some people are wrong. Okay, so with all of these ingredients together, then I can construct a model that basically does this. This is the flow that you should have in mind. I'm starting from a Gaussian and I'm going to move these samples until they end up on the corners. And I might not end up exactly on the corners, but I just take an argmax at the end and I round. Okay, so let's summarize what we've done. So to learn, I'm going to minimize the cross entropy. And in fact, I'm remembering now that there's a typo on this slide. It should be an expectation over that reparameterized time distribution. So it's not really an integral from 0 to 1. It should just be an expectation over time. I use this to learn the denoiser. And then once I have my denoiser estimate, I solve this approximate probability flow. So to solve this equation, I draw an initial sample from a Gaussian. I plug in my denoiser estimate into that conversion formula for the flow that I wrote down previously. I solve this guy up to time 1, and then I take its argmax to recover a sample. Is everything clear?
Yes, for me.
Yeah. Okay. Okay, so this is the setup. It's now kind of simple. Let me show you some results. So here I'm showing you results on LM1B and Open Web Text. These are kind of standard benchmark data sets. They're actually pretty big. So to do these experiments, you need like at least 8 H100s for a week. So it's really like pretty heavy compute. That's actually considered pretty light in language modeling, but it does take a fair amount of compute. And you have to do a lot of ablations to study this stuff. So it really takes a lot of time to do these experiments. So what I'm showing you in this table is the generative perplexity. This is where I use an external pre-trained large model like GPT-2 to measure the likelihood of the text. Lower is better. It means the text is more likely. But there's kind of an issue with perplexity, which is that you can sort of hack it by outputting like really stupid text. Like, so for example, if you just outputted a bunch of periods or like just the word the over and over again, so just like the, these things would have low perplexity. And it's because like periods are likely and the word the is likely. So you need to, in addition, measure something called the entropy. And basically, you want to make sure that the entropy, which is measuring like diversity of the text, is close to the entropy of the data set. And there's a bit of a trade-off between these two. You can sort of make PPL go very low by lowering the entropy. So the name of the game is you want the entropy to be as low, the PPL to be as low as possible while maintaining a certain value of the entropy. And what I'm showing you in this table is that both on LM1B and on Open Web Text, we obtain very good values of the perplexity while maintaining the entropy of the data set. And in particular, our results are basically state of the art in comparison to these quite serious discrete diffusion baselines. Okay, so that's the performance with 1024 sampling steps. So it's quite inefficient, but we get the right answer. We can study the performance as a function of the number of sampling steps. And we're showing our results in red and the kind of the competitors in other colors. And what you see is that while we win at 1024, and while like everybody improves with the number of steps, everybody gets worse as we go to the few step sampling regime. And in fact, our model is no good for a small number of steps. And this is because it's an ordinary differential equation, and I have to actually accurately discretize that equation. So the question that I want to ask now is, can we actually avoid this differential equation solve? Is there a way that I can train a model that does not need to solve a differential equation, but somehow can avoid it entirely? So in fact, there's many existing methods to do so. There's this class of methods that was first introduced by Yang Song and Ilyas Tskever and Prafula Darawal and Mark Chen called consistency models. There's been a lot of follow-up work improving the training stability and things like that. Then there's variants on these ideas called consistency trajectory models, shortcut models, mean flows, etc. We have a framework or a formulation that we call learning the flow map. And I won't go into great detail on this. I can actually give an entire hour-long talk on just flow maps. But in fact, our framework recovers every one of these existing methods in kind of a unified perspective. So we'll show you that there's a single object, which is called the flow map. We can learn that. And there's many different ways to learn it based on different mathematical characterizations. And every one essentially reduces to an existing approach. Okay, so how does this work? Well, I actually would argue that I think this is like the next frontier in generative modeling, and I think that flow map-based models will completely replace flows and diffusions in the near term. So here's the idea. We're going to switch to a different paradigm, which is we're going to try to learn the so-called two-time flow map rather than the flow. So this guy is an object, capital XST, that satisfies XST of XS is equal to XT, where XT is a solution of the probability flow. Okay, so here's the picture that you should have in mind. We can just kind of jump along trajectories. So if we have this object in particular, we can generate a sample in a single evaluation of the neural network just by using capital X01. So this is much, much more efficient than integrating the ODE because in practice, our neural networks are big. Every evaluation of the neural network is expensive. And so when we integrate an ODE, it's actually quite costly. So if we can get it down to a single evaluation or 4 evaluations or something like that, it's potentially like 100 times cheaper in inference. Okay, so here's the picture you should have in mind. Now we're kind of taking that continuous deformation process and we're just breaking it down into these discrete jumps. But we can take jumps of arbitrary size. So we can, go kind of evenly like we're doing now in a few steps. We can jump all the way in one step, etc. And clearly the flow map is well defined. It is just the solution operator of the flow. Okay, so I can just formally write it as this integral along trajectories of the flow itself. Okay, so one difficulty with this guy is that it's not actually clear how to learn it. Unlike the flow, which we were able to characterize as a conditional expectation, it's not clear that this thing has any simple structure like that. So we need to do a little bit of mathematical analysis to understand it a bit further. So the first thing that we can observe is that there's something called the tangent identity, which is that if I take this kind of limiting time derivative, so I take the time derivative of the flow map, and then I take the limit as s goes to t, I find that there's actually an implicit flow inside the map. This shouldn't be so surprising because if I have a flow map, I can take steps of arbitrary size. So in particular, I can take steps of very small size. And if I take a step of very small size, it's basically an Euler step on the flow. So I can always kind of find the flow by taking small steps with the flow map. And this relation here is just saying that when I take an infinitely small step, I get the flow itself. So this is kind of an annoying limiting time derivative that, it would be sort of difficult to compute in practice. But it turns out that if I use this kind of simple Euler-like parameterization here, then I have a very nice relation, which is that VTT is equal to BT. Okay, so I'm going to define this new object, VST, which is like a two-time velocity field. And it satisfies that on the diagonal, when S is equal to T, I recover the flow itself. So here's kind of how you should view this geometrically. On the left, I'm showing the tangent condition. So I can draw tangents to the probability flow trajectories. And when I do so, the slope of those lines is just equal to the flow. And on the right side, I'm showing you a depiction of what this two-time velocity field actually is. So this guy, VST, if I just rearrange the definition of the flow map, I find that it is precisely the slope of the secant line between any 2 points on the trajectory. So I just take 2 points, I draw a line between them. The slope of that line is precisely VST. This guy is sometimes called the mean flow in the machine learning literature. And in particular, you can see why VTT recovers the tangent condition. It's because if I take the secant, quote unquote, between time t and time t, well, that thing is just the tangent, and that is precisely B. Okay, so how can I use this to actually learn a flow map? Well, we can do something that we call self-distillation. So the idea is that I'm going to parameterize my flow map in the following way, using this kind of Euler step-like parameterization. I will train on the diagonal v hat tt using flow matching, and I will self-distill. In other words, I will distill the flow that is implicit in the model into a flow map for s not equal to t. I haven't told you how to do that yet, but here is how you should think about it. I need to learn the entire flow map over the st plane. Learning the flow map is equivalent to learning VST. And on the diagonal, s is equal to t. I have this relation that VTT is precisely the flow, so I can just learn this guy via flow matching. And on the off diagonal, I need to do some kind of distillation. So I'm basically trying to broadcast that diagonal signal to the off diagonal. So the loss function that I will use will look something like this. It will be a sum of 2 terms. The first term is doing flow matching on the diagonal, so it's learning this implicit flow. And the second term is some kind of distillation objective. And it turns out that we can construct 3 options for distilling the flow map using various analytical characterizations that I will get into later. In fact, I will probably just go into one of them because there's enough detail on the language modeling stuff for this talk. But as I said before, I can give a whole talk just on flow maps where I wax poetic about how to choose between the different options for distillation. Okay, so this is kind of the definition of the flow map. Um, I want to learn this guy for language modeling so that I can actually generate samples efficiently. But there's an issue, which is that in my language modeling setup, the flow map does not live on the simplex by construction, right? I start from a Gaussian and then I end at the vertices. So I'm not on the vertices throughout the whole time. Explicitly, I'm off it for sure. And so I can't obviously learn it using cross entropy. So what I'm going to do is I'm going to define an object called the two-time denoiser. Let's call it delta ST. This guy, it's not actually obvious why you would look at this. It took us a bit of time looking for the right definition. But one way you can interpret this is I'm taking like a single Euler step from time s to time 1, but I'm doing so with that two-time velocity field. Okay, so it'll become clear in a minute why I call it the two-time denoiser. But one key result that we can show about this guy is that it satisfies the following identity. Okay, delta st is equal to this kind of like time-dependent term times this integral from s to t of the denoiser. In fact, it's an average of denoisers, and it lies on the simplex. It's not 100% clear just from this relation alone. You can look at the proof in our paper, but you can prove it by checking that everything sums to 1 and that everything is non-negative. So here's the picture you should have in your mind. I have my flow map, which is defining trajectories, and so it's kind of moving from potentially off the simplex to the vertex. And then I have my delta st, which is this kind of two-time denoiser object that explicitly lives on the interior of the simplex. And it maps along some curve until it also ends at a vertex. Okay, so we need to figure out how to actually use this delta st to learn the flow map. What we're going to do is we're going to sort of go back and forth between properties of delta and property of the flow map itself. So the first thing I want to point out is that the flow map satisfies a semigroup property, meaning if I compose it, it's equal to the flow map evaluated at two different times. Geometrically, this says that taking two jumps is equivalent to taking one larger jump. Okay, and the proof is kind of simple. I just apply the jump condition twice. So I jump from S to U, and then I jump from U to T, and that's the same as jumping from S to T. Okay, so what I want to do is try to figure out what is the analog of this semigroup condition for my two-time denoiser. So let's first observe that I can rewrite the flow map in the following way. And then let's observe that, in fact, the two-time denoiser satisfies the following two conditions. The first one is kind of like the tangent condition. It says that on the diagonal, the two-time denoiser reduces to the one-time denoiser. This is, in fact, why we call it the two-time denoiser. And then it also satisfies a semigroup condition. Namely, I can write delta st as a convex combination of delta at s and u and then u and t, evaluated at the appropriate points, where here gamma, this parameter defining the convex combination, is a certain ratio of times. Okay, how do we visualize this? Well, I have a point x. I can take the flow map at that point x. That point x has a two-time denoiser in the interior of the simplex. That flow map xsu has a two-time denoiser. And in fact, my delta st for any s and t can always be written as a convex combination of these other two-time denoisers. Okay, so why is all this useful? Well, it's useful because I can use this kind of semigroup identity to write out an algorithm that we call progressive distillation. So let's remember that all of this is coming from this notion that if I take two jumps, it should be equivalent to one larger jump. Well, you can use this to write down the following algorithm. I'm first going to state it for the flow map setting, and then I'll write it in the two-time denoiser setting where we're on the simplex. Let's say I have a pre-trained velocity field, b hat t, and I want to learn its flow map. Well, I can do so by writing down an objective that's a sum of two terms. The first one is kind of like a flow matching term on the diagonal, and it says that my student, v hat tt, should match the pre-trained teacher. Okay, so this is basically distillation. And then on the off diagonal, I have a student, which is a large jump, and I have a teacher, which is the composition of two smaller jumps. And the reason it's kind of reasonable to use this guy as the teacher is because taking a small jump is easier than taking a big jump. And so the small jump should be learned more accurately, being anchored by the accurate flow on the diagonal. And this enables me to convert these small jumps into larger jumps systematically. Okay, and in fact, you can do this either in distillation form or in direct training form. If I want to train from scratch, all I do is replace that pre-trained teacher by the time derivative of the interpolant. So now I'm just doing flow matching on the diagonal and progressive distillation on the off diagonal. So this is one consistent way to learn the flow map, and this is in fact equivalent to so-called shortcut models in the continuous time limit. Okay, so what I want to do now is use this to learn in my discrete setting. And what I want to do basically is, again, figure out some way to use kind of like KL or cross entropy. So what I'm going to do is try to write down a KL-based progressive distillation algorithm. Sorry, I seem to have a slightly irritated throat, and talking for 45 minutes straight is starting to aggravate it a bit. Okay, so what we're going to do now is we're going to use those semigroup conditions defined for the two-time denoiser to write down kind of a simplex-based progressive distillation algorithm. So I could do it in the following way. It's going to look very similar to what we had before. We have a student on the diagonal, and that guy is being pinned to a pre-trained denoiser on the diagonal, and I'm pinning it with KL because KL is kind of the right metric for these guys in the simplex. Then I have an off-diagonal student, and I'm matching that guy to this kind of convex combination of two smaller steps on the off-diagonal. And again, I'm doing so with KL to kind of effectively capture this one-hot geometry. When you stick all of this together, what you can learn is a flow map that lets me jump along the simplex. Okay, and very similar to how I could do this in kind of direct training form or in distillation form for the flow map itself, I can do the same thing here. And I can actually learn this model from scratch just by taking KL to the one-hot encodings on the diagonal. This is kind of exactly how we learned a denoiser before, but now we're doing it all self-consistently with a two-time denoiser. Okay, so you stick all these ingredients together and you can train a flow map. And this is exactly what we do. So here I'm showing you the perplexity and the entropy, again, for LM1B and open web text. These are those two data sets I showed you before as a function of the number of sampling steps, but now with our flow map. So let's focus on LM1B in the left column. So what we see is that the entropy and the perplexity are kind of maintained across step counts, and they're sort of state of the art in comparison to the diffusion baselines. And then on the right side, on open web text, it's slightly more subtle. But what we find is that we have state of the art results across essentially all ranges. For the one-step flow map, we get a bit of collapse in entropy. We're still working to improve that, but basically everybody collapses in entropy. And then for two steps and beyond, we have very good entropy, and we have basically the best PPL. There's one curve in the top that looks like it has better PPL, which is this dashed line in purple with square markers labeled duo plus DCD. But if you look below at the entropy, you will see that the entropy has completely collapsed. So this is actually outputting kind of nonsensical text that appears very likely. So this is why these metrics are a little bit difficult, and you need to pay attention to both of them simultaneously. So in LM1B, it's very clear because no curves cross, and we have very good entropy across the range, and we have the best PPL across the range. On open web text, it's a little bit more subtle because some of the curves are looking like they have better perplexity, but their entropy is collapsing. And our results are kind of state of the art across all of these ranges, and we're still working to improve the one-step sampler. Okay, we can kind of capture this in table form here. So we're getting very good perplexity and entropy across the range. So you can kind of summarize this as saying that we have competitive or state-of-the-art performance on both of these data sets in both the many-step and the few-step regimes. And we've done a bunch of ablations as well, testing various ways to parameterize the two-time denoiser, what kind of time sampling you should use, what kind of embedding you should use, one-hot encoding versus a pre-trained embedding, things like this. And we really, looked into this quite extensively to converge on our final hyperparameter configurations here. Okay, I just want to give a little bit of a plug that like one of the most interesting things about this is not just faster generation, but that we can do really interesting things with inference time steering and fine tuning. So we have a new paper coming out, should be out this week, where we show how you can do really efficient inference time guidance with flow maps. This is basically up to 50 times faster than all the competing methods. We have another approach that came out kind of around the same time, which is kind of a stochastic perspective on the same problem. One of them is kind of more of a Wasserstein perspective, and one of them is kind of more of a Bayesian perspective. Um, okay, there's a bunch of theory that I also have that points out that there's in fact many different ways to train these flow maps, and they've kind of all been scaled very well at this point, including by NVIDIA, by people at MIT, and we can kind of develop alternative characterizations of the two-time denoiser using Eulerian and Lagrangian PDEs that kind of are sort of inspired by fluid dynamics, and then we can still learn using KL. I don't want to go into too much detail on this now because it gets a bit technical. I think I'll probably just sort of hold off. Maybe I'll point out that there's a bit of geometrical intuition for these different objective functions. And it's kind of nice where like you kind of either use like an advective term from an Eulerian perspective or kind of like a Lagrangian, like moving with the flow term to predict where you're going to end up in the simplex. And you can kind of use this to construct different PDE style KL objectives. And we're still kind of investigating which of these is the best one to learn. So maybe I'll just wrap up there because we're basically at 50-minute time. So this is kind of a long line of work going back to when I was at NYU, working with Michael Albergo and Eric van den Eenden. We had many collaborators, including Seining, Yifan, Willis, and Mark. More recently, I've been working with a bunch of my friends and collaborators at CMU, including Sheil, Aditi, Justin, and Jerry, Sanjit, Rishal, Manan, Kartik. And this project was done in collaboration with some really amazing people from KAIST. So Jinwoo, Seung-hoon, Chen-yuk, and Jae-hoon were all kind of amazing. We basically met them at NeurIPS and then started collaborating on this, and it's been really, really productive and really fruitful. So I'm really thankful that I met these guys. Okay, thanks for listening. That's all I had to say, and I'm happy to take any questions.